I just wanted to show an experiment where Dr. Wang asked me about this higher frequencies, and the experiments you can also see these many higher frequencies, but I don't want to lose time by pulling this down and up because it will take at least 5 minutes, and we don't have much time left, while I would like to finish the fastest exponential decay, okay? This will be the next subject, and I hope half an hour should be enough for that, but it will be a bit time consuming again to calculate it. The problem with it is that you know, we spoke about it. If we are out of the stability limit, the precision will be the best, but it will vibrate quite long before it stops, okay? If we want to stop it fast, then we should be somewhere inside the stable region, okay? And it would be best to have all these roots as close to zero as possible, okay? So we should have as far from the stability limit as possible. So we would like to find those mu values, then actually we want to find the minimum for 1, 2, and 3. The absolute values of these mu 1, 2, and 3, okay? And this will mean that it will decay in the fastest way, okay? And that's the question, that how much it is and how quickly a robot can stop, okay? Clearly, if we are further in, then the positional accuracy will be worse. But on the other hand, we will stop faster, okay? The exponential decay will be faster. So, how we can check that where these are. And that's why I said that you could leave this space empty here, because we can say that let's introduce mu tilde, for example, and we will say that this mu tilde is equal to rho times mu, where actually rho is less than or equal to 1, okay? No. It should be in the other way around, sorry. Rho is less than 1, and we will say that, that the absolute value of mu is at the stability limit. So what we will do, that we will transform this with the mu equals to rho times mu tilde to the mu tilde plane, okay? It's a new complex transformation again. Here we will use again the unit circle. Okay? This is 1, this is I, okay? And now I will do it with blue, okay? Or I hope this blue will be dark enough, okay? So if we have the roots, for example, here, at the limit, okay? I don't know. Maybe even the third one is somewhere here, okay? So we are just at the limit. This will mean that we are within a circle here, okay? And the radius of the circle is rho, and the roots are somewhere here, okay? So actually, this will mean that I denote the absolute value by rho, okay? So when mu absolute is equal to 1, this will mean that mu absolute is equal to rho, okay? Which will practically mean that if the absolute value of mu is rho, then the real part of lambda, which is equal to the natural logarithm of mu, then the real, it is the natural logarithm of mu absolute value times e to the power of I some angle. It doesn't really matter now what is the angle, okay? And if we do it further, this natural logarithm of mu will be equal to the natural logarithm of rho, and since rho will be less than 1, this will be a negative number, okay? And this will determine that x of t will be proportional to e to the power of lambda t, and so it will be in the range of e to the power of natural logarithm of rho times t, or if you transform it further back, then x of t will be in the range of e to the power of the natural logarithm of rho over tau times t, okay? Something like this. I think yes, because tau is also seconds, capital T is t over tau, yeah, that was the way. So we would like to find what is the minimum value of rho, because if you have the smallest value of rho below 1, then we have a negative number there, and then we will have a fast exponential decay, okay? Now, so this will mean that we do the trick that we try to find that place in the parameter plane when these roots in the mu tilde plane are just at 1, okay? And actually it can be found later if we transform it back again to an eta tilde plane, okay? Where actually this transformation will be mu tilde equals to eta tilde plus 1 over eta tilde minus 1, okay? And then these roots will be just somewhere here, okay? Okay? Just at the limit again. So we'll do the limit. Actually, unfortunately, this one will be out in the infinity, but that's another issue, okay? So we are somewhere here. Okay, so this will mean that we try to find this by substituting back into the equation the rho times mu tilde square. So it will be rho times mu tilde to the power 3, then where is it? Minus 2 times rho to the power 3 times, yeah, that's right. Then the minus 2 rho squared times mu tilde squared plus 1 plus d plus p over 2 times rho times mu tilde and plus p over 2 minus d equals to 0, okay? And now we will try to find when mu tilde 1, 2 is just equal to 1, okay? So when it is 1, and we will try to see how much we can push rho down and to go around this stable region and try to find when rho can be the minimum, okay? So now we will have 3 parameters in it, and if we transform it back in the same way as we did it here, okay, then clearly it should be done as we agreed before. A3, A2, A1, and A0. They are all here, okay? And this is 1, 3, 3, 1. Then it is 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1, 1, minus 3, plus 3, and minus 1, okay? And this is the transformation matrix, but here now we have to substitute rho to the power 3 and minus 2 times rho squared times, I hope I do it correctly, yeah, minus 2 times rho squared. Then, where is it? 1 plus d plus p over 2 times rho, and the last one would be p over 2 minus d, okay? Unfortunately, now the expression will be pretty complicated, okay? So we will have, because we cannot add these things. So here for the first one, we will get rho to the power 3 minus 2 times rho squared plus 1 plus d plus p over 2 times rho and plus p over 2 minus d, okay? This will be A3, and now when rho was equal to 1, we could simplify it a lot, but now it remains quite complicated, okay? The next one will be 3 times rho to the power 3, then will be minus 2 times rho squared. I hope I do the matrix well. Yeah. The next one will be negative again. It will be minus 1 plus d plus p over 2 times rho. And the last one will be minus 3 times p over 2 minus d. Okay? Then the next one starts again as 3 times rho to the power 3. Then will be a plus 2 times rho squared. There will be a minus 1 plus d plus p over 2 times rho. And the last one will be plus 3 times p over 2 minus d. And then the very last will be rho to the power 3, then plus 2 times rho squared. Then there will be plus 1 plus d plus p over 2 times rho, and the minus p over 2 minus d. Okay? Now, first you think it is hopeless. And now we should also calculate H2, which is A1, A2 minus A3, A0, A3. Horrible. Because if you start multiplying these, it will become really messy. Even in Mathematica or Maple, or you can try to do anything. But when you start putting them by computer, how these curves look like and these conditions, because actually the limit would be when these are equal to zeros, okay? All one by one. And actually, the A3 equals to 0, which was originally, when rho was equal to 1, this was simply P. And this was the P equals to 0 line. Actually, this will be just pushed a little bit to the right. So these rho values will remain linear, because D and P is still linear. So it will be a straight line, okay? But this line will actually move a little bit to the right, like this, okay? So the condition A3 equals to 0 will be a line which will be moved a little bit away as rho is increased, okay? And then what will happen to A2? Actually, A2 will also move a little bit away, and this will move like this. Okay, this will be the A2 equals to 0. And what will happen with A1? It will also come down a little bit. This is A1 here, okay? If you rearrange it with respect to D, again it will be a straight line, but it will come down a little bit, and quite obviously these lines will actually, okay, this will come like this. This is A1 equals to, I'm sorry, the figure starts getting messy, but you see the original lines will start getting closer to each other. As you increase rho, the region will start shrink, okay? Clearly there are smaller regions. And where will be H2? We know that it must go through these 2 points, okay? So actually, H2 will be a curve like this. It will be somewhere here. This will be H2 equals to 0, okay? And actually, you will get a smaller region, okay? So, how far can you push it? So as you increase rho, these lines will get closer to each other. Also, these will shrink. And where will you get the smallest rho? It's amazingly simple. Okay? I will try to write it here. The region will shrink to a single point as rho is decreased from 1. Okay? So is it clear? When rho is equal to 1, we are at the red curves. You start decreasing rho, and as you start decreasing rho, these lines start shrinking, okay? And the region will become smaller and smaller because you start pushing the zeros further and further back, okay? And now we will see how far you can push them. And it turns out that you can push them as far when the 3 lines will just cross each other. So the critical point will be when all the 3 lines will cross each other at the same point. Okay? So finally, the A3 equals to 0, the A2 equals to 0, and the A1 equals to 0. They all cross each other. And then at that point, H2 will also shrink. So it will be something like this in the PD plane. This is P, this is D. This will be the A3 line. This will be the A1 was the 45. It will go like this. This will be the A1 equals to 0. This will be the A2 equals to 0, and they cross each other at the same point, okay? And actually, the H2 will also go through that point. And this will be the rest of the stable region. And otherwise, this will be the region, for example, for rho less than 1. And this I will put it with red when rho equals to 1. Okay? This is when rho is equal to 1. Okay? This is rho equals to 1, rho less than 1, and in the middle here, rho equals to rho minimum. Okay, so that will be the point where all the three will cross each other. So now you can say that finally we can find this rho equals to rho minimum if these three equations are fulfilled. But these three equations have three unknowns, P, D, and rho. Unfortunately, for rho it's third degree, but for P and D it is linear, so we should be able to solve it. Okay? So let's see. If I introduce new variables, say, I don't know, just for the sake of simplicity, I will use capital A. Let capital A denote the 1 plus D plus P over 2. Or actually, this 1 plus D plus P over 2, it is just, which one? It is A, no, it's nothing, okay. 1 plus D plus A over 2, and let's denote by B the P over 2 minus D. Then these three equations will look like rho to the power 3 minus 2 times rho squared, then plus A times rho, and the last one will be a plus B equals to 0. The next equation will be rho to the power 3 times rho to the power 3 minus 2 times rho squared, minus 2 times rho squared, and what is the next one? Minus A times rho, and the last one is minus 3 times B equals to 0. And the last equation will be 3 times rho to the power 3 and plus 2 rho squared and minus A rho and plus 3B equals to 0. Okay? So three equations, three unknowns. Three equations, three unknowns. And since A and B are linear, we should be able to get rid of them. Okay? For example, very simply, if we add the two first equations, then from the first two, what shall we get? A times rho will cancel, but I don't want to make a mistake, so I have to check it again, not to make a mistake. If you add the first two equations, so it's rho to the power 3 minus 3 plus A times rho plus B, good. 3 minus 2 minus A rho minus 3 times B, that's also good. So minus A rho and plus 3, yeah, it looks good. So if I add the first two equations, then I will get 4 times rho to the power 3 minus 4 times rho squared, and this will cancel, and I will get minus 2b equals to 0. Okay? Then let's try to get rid of A from these two equations. then I have to subtract from the, I will subtract from this that, okay? Then A will cancel again, and I will get 4 times rho squared, and this will cancel, this cancelled, and it will be plus 6b. Okay, and this was minus 2b. Okay, then what to do? Multiply it by 3, okay, and add the 2 equations, okay? And so if I multiply by 3 and I add the 2 equations to each other, then it will be 3 times 12, it will be 16, no, sorry, it will be 12 rho to the power 3. Then there will be minus 12 plus 4, which is minus 8. Minus 8 rho squared and 0 equals to 0. So actually, I am so lucky, again, that while it is a 3rd degree polynomial for rho, I can still solve it. First, it gives the impression that rho could be 0, but actually rho cannot be 0. It would mean that all the 3 characteristic roots are 0. And if you look at the equation, it is impossible. So here, if mu is equal to 0, it will not be equal to 0 anyway, okay? So it's impossible. That's a 4th root. So actually rho cannot be equal to 0, which will mean that rho is equal to 2/3. Isn't it beautiful? Rho is equal to 2/3. So we already know how fast the fastest decay can be. I just have to calculate the natural logarithm of 2/3, okay? And this will be, anyway, I will write it later. It will be quite nice again. But let's calculate where is this optimal point. If this is like that, then B will be equal to, so rho minimum is equal to 2/3. And then B is equal to, it's 2/3 times rho squared, okay? 2/3 times rho squared, so it's actually 8/27, okay? Because it will be 2/3 to the power 3. And how much is A? I don't know which equation we should use, but A is not easy anyway. A is equal to, if I put those things to the other side, then it will be minus rho squared plus 2 rho and minus B over rho. So it will be minus 4/9 plus 2 times 2/3 is 4/3, and minus, oh my goodness, 8/27 divided by 2/3, it must be 4/9, okay? So, I don't know, it's 9, and this should be minus 8 plus 12 is 4. I think it's 4/9. Okay, so it's 8/27, 4/9. And now we should just solve this. So it means that 1 plus d, where was a and b defined? 1 plus d plus p/2. It is equal to 8 over, no, it's equal to a. It is 4/9. I hope I did it correctly, isn't it? No, it's impossible. It cannot be 4/9. It's 12/9. No, it's 4/9. I think it is correct, yeah? Gee, please. Okay, it's 4/9. And the other one is p/2 minus d, which would be 8/27, okay? And now if we add the 2 equations, then we will get p. This P will be important because this will say that if we have this fast decay, how much will be the position error. So if we add the two, it will be 4 over 9 plus 8 over 27 and minus 1. Okay? So all in all, it's 27, and it will be 12 plus 8. My goodness, we got a negative value, it's not good. 12 plus 8. No, I did something wrong then. I was in a hurry, I should have checked it better, but I worried that I did something wrong. It's rho is 2 over 3, then P over 2 minus D, it should be minus 8 over 27. B, it should be negative. Of course, okay, here, if I solve it for B, it should be negative. It's minus 8 over 27. No. It's minus 8 over 27, okay? I will do it with red because I made a mistake. So if you want to correct it in your lecture notes, it's minus. It's minus 2 over 3 rho square, okay? Which will mean that it is, here it will be plus 4 over 9, which will mean that that part will be 4 over 3, isn't it? Yeah, it's 4 over 3. I'm sorry, it's 4 over 3. Okay, because these two will cancel, it will be plus 4 over 3. So then it will be minus 8 over 29, and it will be 4 over 3. Okay? And then if I add the two, it will be 4 over 3 minus 8 over 27. Then all in all it is 27, and now I will try to do it again. If it is, it's 9 times, it's 36, okay? Minus 8 minus 27. Oh, that's much better. I worried about it, that it will be negative, but now it's just positive, okay? It's 1 over 27, because it's 36 minus 35, and P is 1 over 27. And now actually if you do D, you will substitute it back there, and so on and so on. It will be 17 over 55. Over 54, sorry. Over 54, okay? We will run out of time. I don't want to spend your time much on this, but it means that this point, this optimum point, is actually at 1 over 27 and 17 over 55, okay? Which means that actually we have a fast decay, but delta will be 27 times C over m times tau square. So it is much, much larger than the 4 times C over m times tau square, what we had in the optimum case. But in this case, we had long transient vibration, because it will oscillate a lot before it will stop. And here we have a short transient, or shortest transient. And the shortest transient will be actually characterized by an x of t, which is proportional to the e to the power of the natural logarithm of 2 over 3 divided by tau times t, okay? So this will mean that it is e to the power of 1 over tau times the natural logarithm of 2 minus the natural logarithm of 3. No, it will not be good. How is it? ln 2 over 3. 693. Yeah, correct. It's fine. Okay? Times t, times the regular time t. Okay? ln 2 is 0.693. We already did it yesterday. And this one is about 1.193 or something. So all in all, it is e to the power of minus 0.4 over tau times t, okay? Or you can also write it that it is e to the power of minus 0.4 times the sampling frequency times t. Okay, 1 over tau is the sampling frequency. So it means that if you increase the sampling frequency again, it will stop faster. So to have a faster computer is very good, because here, if the sampling frequency is larger, if it is 100 hertz, okay, then, so again, if fs is equal to 100 hertz, okay, then x of t will be proportional to e to the power of minus 40 times t, okay? While if it is 1 kilohertz, then x of t will be proportional to e to the power minus 400 times t, okay? So it will decay much faster, but it will not be like the position error is actually proportional to the square of it, but this one is just linearly dependent on fs. But here you have to see that the error is much larger, okay? The error is much larger. It's 6 times, the position error is 6 times or almost 7 times worse, okay? 7 times worse. So instead of, say, 1 millimeter, it will stop with 7 millimeter accuracy, but it will stop quickly, okay? So that's why last time when I ended the lecture, I ended it this way. So we have 2 possibilities at the moment, and if you have any idea how to make it optimal, or you have an optimal criterion for that, to find an optimum between these 2 points, because this is the best point for settling signal, this is the best point for accuracy. So if we have the red curve, okay, the red curves mean that we have long oscillations for a long time, okay, very small decrease, but finally it will stop very precisely, okay? It will stop very precisely, because this error will be very small, okay? While in the case of the blue curve, okay, we will stop much faster, but with a large value, with a large error, okay, much larger, or 6 times larger error actually. This error will be much larger than this one, okay? So we will have a fast decay, here we have a slow decay, okay? So that's the, and somehow you can try to develop an optimum criterion, and I think this is a much more important optimum criterion than the classical LQR algorithm where they try to minimize with the energy and how much energy is used in the structure. Actually, it also gives a limitation for the proportional gain P, but I think the real limitation is related to the sampling time and the time delay. Okay, so thank you very much for today, and next time we will start with some practical conclusions. Thank you indeed.